10.3, the cross product and dot products. We already just went through the definition of dot product the last time. So this time we will take a look at the mathematical expression of cross product, and that's its a mathematical definition too. So if you do the dot product out of two vectors, that result in the scalar quantity, but if you even a cross product of two vectors normally produce that the another vector. So vector cross product vector equals another vector. They normally just orthogonal to original two vectors. So their direction of the new vector produced by the two vectors normally perpendicular to original two vectors. So I'll give you the full expression of the cross product out of arbitrary two vectors. Those vectors are defined with the xyz component. So I will show you how those xyz components out of two vectors mixed into the resulting vector out of the cross product. So 10.3, let me change the color of the pen. So basically 10.3 is cross product. So let's just u vector defined with the u1 I for x component, u2 j y component, u3 k g component, and another vector v, same thing, v1 I for x component, v2 j y component, v3 k g component. So cross product out of these two vectors basically expressed with the matrix. So u cross products is b defined by matrix. So the first row of this matrix consists of unit vector I, j, k, and second row has the xyz component of u vector, and third row is out of the b vector, second vector, b1, b2, b3. So I think you're already familiar with how to do this 3x3 matrix operation, but let me remind you how to do it. The first step, let me change the color of pen. For x component out of this one, you have to reduce that the 3x3 to the 2x2. But first step, you have to delete of column and row out of the x component. So you take that out of the 3x3 matrix, only leave the 2x2 matrix of non-x elements. So that is I times u2, u3, b2, and b3. Here, one thing you have to make sure, you gotta just multiply this sign indicator -1 to the power of 1 plus 1. That is usually, this one is the column number, and this is row number. You gotta just add it, then that's it. And the second j, same thing. You have to pick up the non-y component out of second and third row, and this one, this one, this one, this one, and that is u1, u3, and the b1 and b3. Same thing. You have to multiply the sign indicator, and the power of that -1 should be 1 plus 2, because the j is first row and the second column. So that should be, this should be I, this is j. And number 3, k. G component out of this. Same thing. You have to pick up this non-Z component out of 3 by 3 matrix. So that is U1, U2, V1, V2, and multiply by sign indicator minus 1. So that the power of that sign, it should be the 1 plus 3. So that is I, and that is J. So from that, this linear expression should be given by algebraic expression out of this 2 by 2 matrix reduced form of the 3 by 3 matrix. So this one, minus 1 to the power of 2 is positive 1, and this one is negative 1, and this is positive 1. So eventually this equation should be simplified this form. So now you know how to do the 2 by 2 matrix operation, right? So from that 2 by 2 matrix, you can find that the coefficient for the unit vector I, so that is U2 times U3, V3. The V3 minus U3 times V2, I minus U1 times V3 minus U3 times V1, J plus U1 times V2 minus V1 times U2, the K. That is full algebraic expression of the U cross product V vectors. So that is resulting cross product vector. You can sometimes just plug this minus sign into this formula, so you can actually stay consistent with their expression. So that should be U2 V3 minus U3 the V2 I plus U3 V1 minus U1 V3 times J plus U1 V2 V1 and U2 the K. So that is full expression of the U cross product of V. Okay, so let's take a look at the example to find out how to use this formula. So the example is number 1. The U vector is I 2J plus K. So its terminal point of this vector is 1, 2, 1, and the V equals 3I J plus 2K. So the terminal point is 3, 1, 2. So now let's take a look at the U cross product V out of this. U cross product V is I J K 1, 2, 1, 3, 1, 2. So that is what? I equals 2 by 2 minus 1 by 1 plus J equals 3 by 1 minus 1 times 2, and plus K is 1 times 1 minus 2 times 3. So that is 3I J minus 5K. Now, let's check the resulting cross product is same with the changing order of U and V. So now you want to estimate, calculate the V cross product U. So you kind of like reverse that the order of U and V vector in cross product. So that is I J K 3 1 3 1 2 and 1 2 1. So now I is 1 minus 4 plus j is 2 minus 3 plus k is 6 minus 1. So that is minus 3i minus j plus 5k. So now if you take the minus sign out of this, then it's minus 3i plus j minus 5k. That is exactly same as vector u. So that is minus, that is the u cross product v. So that is same as minus u cross product v. So this result is showing you that if you just change the order of the two vectors in cross product, that actually bring up the minus sign. So changing that the sequence of cross products, it just induced that the minus sign to the resulting vector. So if you want to figure out that opposite direction of cross product, all you need is just take the minus sign in front of that the resulting vector. So now let's take a look at the cross product out of same vector. So now you want to just cross product v to the v. So take a look at how it works. So now that is I, j, k, and that's I is like 1. The second row is 2, 1. So the row is same 1, 2, 1. So that is I is the 2 minus 2. The j is 1 minus 1, and plus k is 2 minus 2. So all the coefficients in front of like unit vector I, j, k are same as 0. So that results in the 0 vector. So if you cross product the same vectors, then that produces that the 0 vector, and then not, no numbers that's 0 on their element. So let's take a look at the properties of cross product. It will help you to understand how it works with the other types of vectorial operations. So number 1, algebraic property of cross vector. Algebraic property of cross product. Number 1, as I already showed you, the cross product of two vectors could be same as minus of the cross product, but in opposite sequence. And number 2, if you cross product to the summation of two vectors, then the cross product could be applicable to each vector inside the bracket separately. Number 3, scalar quantity could be applied to or multiplied to two vectors with the cross product, but all you need to actually just multiply scalar quantity to one of those vectors. It doesn't matter the one before, one or one after. All you need is actually plug that scalar quantity into one of those vectors, then that result should be same. So that is C, U cross product V, or U cross product C, V. They all should be same. Number 4, obviously, if you just cross product 0 to the V, any vector, that should result in the 0 vector. Number 5, now I already mentioned, if you cross product the same vector, that results in a 0 vector. Number 6, and now you have dot product to the cross product to the resulting vectors out of the cross product, then that should be same as so that basically that combination of dot product and the cross product could be applied to the same vectors, but in opposite direction. So that should be a u dot V cross product the W same as the U cross V dot W. That should be same. Okay, so that is the interesting actual property of the cross product. So the combination of dot and cross product, it just stay the same, even if there's applied three vectors, opposite opposite way. And now next property is geometric property. Geometric property. Geometric properties. So number one, geometric property of the cross product. Normally, the cross product is orthogonal to both u vector and the v vector. They should just perpendicular to each vector same time. So if you draw that three vectors, you have u vector, this is v vector, and their angle is theta. So if you just cross product u and v, then resulting vector, maybe w, should be orthogonal to v vector and u vector at the same time. And because of that too, the magnitude of this cross product is same as the magnitude of multiplication of magnitude of each vector times sine theta. Here's the theta is the angle between the u and v vectors. Okay, so number three, if and only if the u and v vector are scalar multiples of each vector, then u vector times v vector should be equal to 0. So I can just actually prove this idea. So if, for example, u vector is multiplication or multiple integer of the the u vector, like this. So here n is scalar integer. Then u cross product of v should be 0. So now let's just replace v with this and u. Now that is n u, and n scalar quantity could be out of the cross product. So that is n times u cross product then u. So now you cross product to the same vectors. So that should be equal to 0. So that n times 0 equals 0. Okay. And usually number 4, the magnitude of cross product of two vector u and v is normally area of the parallelogram having u and v as adjacent sides. So that is, you have u vector and angle theta, this is v vector. And if you do u cross product of v, then that should be normal to those two vector. But if you take the absolute value out of the cross product, then that is same as area of this parallelogram that has the two vectors as a side of this rectangular parallelogram area. Okay. right? So let's take a look at the example. So example number 2. Example number 2. So here, u vector is 3i minus 4j plus k, and the v vector is minus 3i plus 6j plus 0k. So terminal point of these two vector is 3 minus 4, 1, and minus 3, 6, 0. So let's take a look at the cross product out of these two vector. U cross product B equals, now I j k is 3 minus 4, 1, and minus 3, 6, 0. So x component in I is minus 4 times 6 minus 6 times 1, and plus j y component in j is 1 times minus 3 minus 3 times 0, plus k is minus 4 times minus 3 times 6, 3 times 6. So that is the 6 minus 6i plus minus 3j and plus 6k. Okay. Oh, here, this one should be first. That 3 times 6 minus 4 times minus 3. So that is the cross product out of the two vectors. And the magnitude of this vector is now is 3. If you take a 3 out of this, then that should be minus 2i minus j plus 2k. So from that, magnitude of this cross product is 3 square root of 2 square plus 1 square and the 2 square. So that is 3 times square root of 9. So that is 9. And so unit vector of this cross product, or normal vector of u and v, should be normalize the cross product with the magnitude of a u cross product v. So that should be u cross product v normalized by the magnitude of those vector should be 9 over 1 over 9 times 6i minus 3j plus 6k. So that is minus 2 over 3i minus 1 over 3j plus 2 over 3k. That is unit vector. Let's see, that is w. The unit vector w, which is orthogonal to the un, the v. Okay. So next one is, that is the example to understand how the cross product works in the three-dimensional space. And we want to actually expand the idea with 3 different vectors. So if you combine the dot product with the cross product, that produce a three-dimensional object out of three different vectors. So that is called the triple scalar product. So that scalar product consists of three vectors and a dot and cross product. So assume that you have three vectors, which is u1i for x, u2j for y, u3kz, and the v vectors, and the v1i, v2j, and the v3k, and the z vector, w vector actually is w1i, w2j, w3k. So if you do triple scalar product, which is u dot product times v cross product w, then that should be expressed with the matrix form again. That is u1, u2, u3 in the first law, and the v1, v2, and v3 in second law, and W1, W2, and W3 in third law. So you know what to do this, right? So basically it is U1 times V2 W3 minus V3 W2 plus U2 times V3 W1 minus V1 W3 plus U3 V1 W2 minus V2 W1. That is result of the triple scalar product out of the dot and cross product. So if you draw this one, first step, you have to just create the cross product out of the V and W vector in three-dimensional space. Now you have two vectors. Okay, so let's take a look at U and W vector first. If V vector is this direction and W vector is this direction, then dot product of these two vectors should be this direction, orthogonal to this U vector and V vector and W vector, then is V cross product W. And now the U vector is just pointing that this direction. Then this vector U could be projected onto the this cross product of V and W vector. So that's normal. So now, as I said, the magnitude of the V and W vector is the area of parallelogram right there. And this amount of the length of this projected arrow out of the U is the magnitude of projected vector of U onto the U cross product W. So now the triple scalar product is basically this projected the vector out of U with this area, so that actually correspond to the volume V. So the area S is, as I said, this is the area of base. That is the magnitude of cross product V and W, and the volume is usually the volume of the parallel pipe, which is made out of the three vectors. So that is actually correspond to the U, the three scalar product from the U, V, W. So if you take that the cross product, three scalar product, that is same as the volume V of parallelogram that is made out of the three vectors. So we can estimate that the volume of this U and V and W with the example. Let's take a look at the example first. So that is example 5, and U vector is 3i, 5j, and the k, and the V vector is 2j and 2k, and W vector is what? 3i, j, and k. From that, you can easily estimate the volume of that with this triple scalar product, which is 3 minus 5, 1, 0, 2 minus 2, and 3, 1, 1. So from that, the answer is 3 times 2 times 1 minus 1 times minus 2 plus minus 5 minus 2 times 3 minus 0 times 1 plus 1 times minus 2. No, not minus 2. That it should be 0 times 1 minus 3 times 2. So that result in 36. So that is volume of the parallel pipe made out of these three vectors.